Hello, good morning friends. Welcome to e-learning program. Now, today we will discuss a topic of mathematics which is related to abstract algebra. In abstract algebra, today we will discuss a subtopic group and subgroups. But before going to groups and subgroups, there are so many definitions, so many things, terms, events which are related to groups. The first of all, sets. Sets, generally in general life we say, in general life sets, that means the collection, but set, mathematical definition of set is a well defined collection of objects is known as set. Now, the word well defined means by which we can say that either elements belongs to the set or does not belongs to the set. But well defined collection and collection, what is the difference between well defined collection and collections? Well defined collection, that means the collection of all BSc students, that means it is well defined because they are the students of a BSc. Now, a collection which is not well defined, can you tell me an example of a collection which is not well defined? Otherwise every collection becomes a set, but set which is a well defined. So, a collection, we can take an example, a collection which is not a set, that means which is not a well defined collection. Collection of all beautiful girls, is it a set or not? Not, it is only collection, it is not a set. Why? Because it is not a well defined. In my views someone is beautiful, but in other views he is or she is not a beautiful. So, there is no definition of the beautiful. So, it is not a well defined. Similarly, the collection of intelligent students is also a collection, but not a set. Why? It is also not a well defined. There is no definition of intelligence. Some students which are intelligent in some subjects, but they are duffer in other subjects. So, intelligence, there is no definition of intelligence. So, collection of all intelligent student is not a set, it is only the collection. So, finally, a well defined collection of objects is known as a set. We are not going to deeply in the set because our topic is related to groups, but in groups a set becomes a groups after satisfying some conditions. We will discuss one by one. Now, before group there is a binary operation. We can also say that binary composition. Binary composition is a special type of a function, Now, you ask me what is the function? So, we will discuss everything on the board.
Yes, rolling.
Yes. See, set, this is the set, we denote it by capital A. The another set we denote it by capital B. These are the sets, the elements A, B, C are the small letters. These are the elements of the set. We can write it as A is equal to A, B, C. Similarly, the set B in which E, F, G, there are 3 elements in B and 3 elements in A. It is not compulsory that these two sets have the same elements, same number of elements, they may be different. Now, we will discuss the function. Function is a rule by which every element of the set A is associated with the elements of B is known as a function. We can show it as f, and we can write it as f is a function from A to B. That means f is a transformation. Somewhere we can write it as transformation, mapping. So f is a function which maps the elements of A into the elements of B. That means there is an association between two sets A and B. We can again repeat the definition of the function: a rule by which every element of A is associated with elements of B uniquely, then this rule is known as a function from the set A to the function to the set B. We can write it as f A to B. Now, binary operation, we will discuss about binary operation, which is very important for the group. So, binary operation is a special type of the function. We will discuss the binary operation by taking the group. Let G, the first word of the group G, is the notation of the group. G is a group. G is a non-empty set. It is mandatory for group, it must be non-empty. G is a non-empty set, and G is said to be a group with binary operation star. Star is the notation if it satisfying the following properties. We will discuss later on. First we will discuss the binary operation. Now, what is the binary operation? By the name binary, that means there is the relationship between two. Binary operation, in binary operation we can take two elements of the set and apply the operation on these two elements. The third elements must be the same of the same set. For example, n is the set of natural number. We can write it as n is the set of natural number. We can take the binary operation plus. If we add two natural numbers, then we can get the resulting one is also a natural number. So, plus becomes the binary operation on the natural number. We can take any two natural numbers and add these two numbers, we get the resulting one is also a natural number. That means binary operation, it is denoted by star and apply on G cross G, and resulting is G, where G is any non-empty set. G cross G means we can take any two elements of the set G, G cross G, two elements of G. One and, for example, we can take 1 and 2 are the two natural numbers. If we apply the addition on 1 and 2, then we can get 3. 1 plus 2 is equal to 3. 3 is also a natural number. So, plus is a binary operation on natural number. In the same, we can take the binary operation as negative. Is it binary operation or not? It is a operation, but it is not a binary operation on natural number. For example, if we take 2 and 1, both are belongs to natural number. But 1 minus 2 is equal to minus 1, which is not a natural number. So, minus is not a binary operation on natural number. Multiplication is a binary operation on natural number, but division is not a binary operation on natural number. So, binary operation, that means we can take two elements of the set, apply the operation on these two elements, we get the third element, the resulting elements must be the same set, then we can say that the operation is a binary operation. Otherwise, it is not a binary operation. Theoretically, we have to represent binary operation by star, is a special type of function on G cross G to G. Now, properties of binary operations. We will discuss one by one. The first property of the binary operation is closure property. In this property, let A B belongs to G, then A star B is also belongs to G. It is the definition of the binary operation. First property is also shows the definition of the binary operation. We can take two elements A, B of G. We apply the binary operation star on A and B. The resulting element must be the element of G. Second property, associative property. In associative property, we have to take three elements of the set G. Let A, B, C belongs to G. Then A star B star C must be equal to A star B star C. This property is known as the associative property of binary operation. Now, the third one, commutative property. Let A B belongs to G, then A star B is equal to B star A, then this star satisfies the commutative property. Fourth one, existence of identity. Let A belongs to the set G, then there exists an element and unique element, an element but it is unique. Then there exists an element E belongs to G such that A star E is equal to E star A is equal to A. For every A is belongs to G, then E is called the identity element of the set G. The next one, fifth property, inverse property. In inverse property, due to the binary operation, if we can take any element of the set G, then there exists another element which we can apply on the same one, then resulting one is the identity element. For example, fifth one, existence of inverse. Existence of inverse property. Let A belongs to G, then there exists a unique element B belongs to G such that A star B is equal to B star A is equal to identity E. E is the identity element according to the fourth property. Then B is called the inverse of A and vice versa, that means A is inverse of B. Now, the next, after binary operations, we will discuss the algebraic structures. Algebraic structure is the one more powerful than the set. In a set is a well defined collection, but in algebraic structure, a set equipped with a binary operation star is known as algebraic structure. Recently we discussed G is a set, G is a non-empty set, star is a binary operation on G. Then after combining these two, G star is known as algebraic structure of the set G. G is a set, G is a non-empty set, star is the binary operation on G, then G star is known as algebraic structure of G. After algebraic structure, we come to our point group. Now, the group. Group, we can denote it by capital G, the first word of group. A non-empty set G equipped with binary operation star is known as a group if it satisfying the following properties. That means for a group it must be a set and it must be non-empty, and there is a binary operation, it is denoted by star. That means it must be an algebraic structure, and after algebraic structures, if it satisfying the following properties, then it becomes a group. These properties are, first property is closure property. We already discussed in binary operation of these properties. That is, A B belongs to G, then A star B is also belongs to G. Second, associative property. A B C belongs to G, then A star B star C is equal to A star B star C. For third, existence of identity. Let A belongs to G be arbitrary, then there exists a unique element E belongs to G such that A star E is equal to E star A is equal to A. Then E is called the identity element of the group G. The fourth one, existence of inverse. Now, the fourth property, existence of inverse. In this property, every element have their inverse in the same set. For example, let A belongs to G, then there exists a unique element B belongs to G such that A star B is equal to B star A is equal to identity, where E is the identity element of the group G. That means a set, a non-empty set with binary operation star is said to be a group if it satisfying these four properties. First one, closure property; second, associative property; third, existence of identity; and fourth, existence of inverse. If the set non-empty set satisfying all these properties, then it becomes a group. Now we will discuss an example of a group, a very simple example, set of integers. It is denoted by capital Z. Set of integers is denoted by capital Z. We apply the binary operation plus on this set of integers. Z is equal to 0, 1, 2, 3, 4, so on, minus 1, minus 2, minus 3 and so on, set of integers. Show that Z is a group with binary operation addition, that is plus. So first set of integer is a well defined, that means it is a set. Second, 0, 1, 2, 3, 4, 5 all are the elements of the set Z, that means it is non-empty. Addition is a binary operation on integers. If we can take two integers and add these two elements, the resulting one is also a integer. For example, 0 and 1, 0 plus 1 is 1, is also integer. 2 plus 3 is equal to 5 is a integer. Minus 2 plus 1 is minus 1 is again a integer. So plus is a binary operation on Z, that means set of integers. Now we will discuss the properties, the remaining properties, that means closure property, associative property, existence of identity and existence of inverse. So first one, the closure property. Closure property. Let A B belongs to Z, then A plus B is also belongs to Z by the definition of the binary operation. First property is proved, already proved by the binary operation, because in binary operation if we can take two elements of the Z, then the resulting one is also an element of Z, that means A B belongs to Z, then A plus B must be belongs to Z. So closure property is satisfied. Second, associative property. Let A, B, C belongs to Z, then A plus B plus C is always equal to A plus B plus C. You can take any three integers according to your choice. Suppose we have to take three elements 2, 3 and 5. We find 2 plus 3 plus 5 is equal to 10. 2 plus 3 is 5, 5 plus 5 is 10. Now we have to add these three elements, 2 plus 3 plus 5 is again 10. So associative property is satisfied in integers. The third one, existence of inverse. Third, let A belongs to Z, and we know 0 is also belongs to Z. In integer 0, 1, 2, 3, minus 1, minus 2, minus 3, minus 4. A is integer, 0 is also integer, and a plus 0 is equal to 0 plus a is equal to a for every a belongs to z. There is no change if we have to add 0 in any one of the integer. So this 0 is called the identity element of the set G. So 0 is called identity element of Z. Hence, existence of identity property is satisfied. Next, the fourth one, the last one, existence of inverse. Let A belongs to Z, then minus A must be belongs to Z. If A is positive, then minus A is the negative one. If A is negative, then minus A is positive, negative, negative, positive. For example, 2 is belongs to Z, then minus 2 is also belongs to Z. 2 is a positive integer, minus 2 is a negative integer. So A belongs to Z, then minus A must be belongs to Z, such that A plus minus A is equal to 0. 0 is the identity element. If we have to add these two elements A and minus A, the resulting one is the identity element, then we can say inverse of A is minus A and inverse of minus A is plus A. So inverse property is satisfied. So all these four properties are satisfied. So Z becomes a group with binary operation addition. Now the same set, but we have to change the operation. We have to change the binary operation. In place of addition, we have to take the multiplication. Then we see is Z is a group or not. A question may be asked, show that Z set of integers is a group or not with binary operation multiplication. Show that set of integers is a group or not with binary operation multiplication. Set of integer, we already discussed in the previous example, is a set and it is non-empty, and operation is multiplication. We have to multiply the two integers, the third one is again a integers. Suppose we have to take 2 and 5 are the integers. If we multiply 2 and 5, the resulting one is 10, which is also a integers. So Z set of integer is a non-empty set and multiplication is a binary operation on set of integers. Now we see the properties are satisfied or not. If set of integers with binary operation multiplication, all the properties are satisfied, then it becomes a group, otherwise it is not a group. So one by one we will discuss. The first one, closure property. Let A B belongs to Z, then A into B is also belongs to Z. A and B are the two integers. We apply the multiplication on these two integers, that means A into B, the resulting one is also an integer. So, closure property is satisfied. Second, associative property. Let A, B, C belongs to Z, then A into B into C is always equal to A into B into C. A, B, C are three integers. If we multiply these three integers, either first A or B or first B and C, the result of both sides are the same. That means the associative property is satisfied. The third one, existence of identity. Let A belongs to Z. A is an integer. It may be positive, it may be negative, or it may be 0. We know 1 is also belongs to Z. 1 is an integer. If we apply A into 1 is equal to 1 into A, the resulting one is A. A may be positive, may be negative, or may be 0, but we have to multiply A with 1, then the resulting one is the same element A. Therefore, 1 is known as the identity element of G. Thus, 1 is identity element of Z with respect to the multiplication. Now, the fourth one, existence of inverse. Existence of inverse. Let A belongs to Z, then suppose B belongs to Z such that A into B is equal to 1. So, B is equal to 1 by A. B into A into B is equal to 1, then B is equal to 1 by A. A is an integer, then 1 by A need not be an integer. If we have to take A is equal to 2, then 1 by 2, is it integer or not? No. B is the inverse of A, but B is not a integer. It is not mandatory that B must be integer, it may be non-integer value. So, the fourth property, existence of inverse property, is not satisfied for every integer. It is only satisfied for only 1. 1 into 1 is equal to 1. 1 into 2 is equal to 2, not equal to 1. So, inverse property is fails, so it is not say group, but it is satisfying. Overall we see Z is a set. First, Z is a set. Second, Z is an algebraic structure because it is equipped with binary operation. Third, it is not a group, but it is a semi group because it satisfies these two properties. A algebraic structure which satisfies only two properties, a closure property and associative property, then it known as the semi group. So, set of integers with binary operation multiplication is not a group, but it is a semi group. Any doubt? If you have any doubt, then you can ask without any hesitation.
Yes.
So, dears, you see, today in this lecture we have to discuss about the definition of the sets, algebraic structures and groups with the help of the some examples. Now, in the next lecture we will discuss some other examples related to the groups, related to with different binary operations and subgroups. So, you are requested to subscribe and you can learn more and more from these e-learning programs. Thanks to all. Okay, best of luck.